My name is Roar Bakke. As rightly said, I work in Gexcon. I actually have a slide which is like a CV, but it's too detailed to go into, but I'll just show it briefly. My key qualifications are those of working with explosion and fire safety, process safety, technical safety, and risk analysis. And I've done this since I graduated from university back in 1981, so it is more than 40 years now. I've been associated with Gexcon for most of this time, but I've also spent a significant time with the Norwegian state oil company, now called Equinor. Earlier it was called Statoil. I'm also a professor at the University of Stavanger, where I teach technical safety. So I think that should be enough. This presentation is really an extended version of the presentation that I gave at the Sri Lanka Green Hydrogen Symposium back in November. So some of the slides that I will be showing you will have seen before, but definitely not all of them. The contents of this webinar is to some large extent based on work from colleagues in Gexcon, so a big thanks to them. They have supplied some of the material that I will be showing today. I understand that there is some time allotted to questions and discussions afterwards. So in order for me to be able to finish my presentation in roughly an hour, then please let us keep the questions for the end session. Hydrogen is not a new energy carrier. It has been widely used in refineries and chemical plants and has also been used in aerospace industry, and this for decades. So why are we focusing so much on hydrogen safety now if it has been used so long? Well, the reason is that until now, hydrogen has been used in, let me call it, controlled industrial environments where there are strict safety regulations. The requirement now to decarbonize our global economy means that new applications for hydrogen are being developed, bringing it out from these industrial controlled environments, entering into society, into the community. This is why we need to develop a safe design for the new applications of hydrogen and based on an understanding of chemical and physical properties. Well, is it safe? The reason why we are focusing on hydrogen is, of course, its great potential as a clean and versatile energy source. And producing it, in particular from renewable sources, makes it a very valuable alternative to fossil fuels. And as I've said, but unlocking its potential requires addressing safety concerns associated with not only production and use, but also storage and transportation. Studying historical incidents will help us identify root causes, develop safer technologies, and implement effective safety measures. And experts can then establish best practices and guidelines to prevent accidents in the future. For example, you can find information about hydrogen incidents on the website h2tools.org and under Lessons Learned. What is very important is to realize that accidents will happen. Risk will never be zero. We are striving to make it as low as we can, but it will never be zero. So when an accident happens, or even just a near accident, investigate and learn from them. That is how we can avoid it happening again in the future. As was mentioned, there are 4 parts to this presentation. The first one is examples of hydrogen accidents. Then the second one will be hydrogen safety characteristics, fires and explosions. The third will be analysis and control of risk, and the last one will be on safety regulations. So I will start with the hydrogen accidents. I don't plan to go into a lot of detail. Time does not permit, and I probably don't have the necessary insight to really go into the depths of all these accidents. But you can find information online, relevant information, and quite detailed about the different accidents. The first one that I will address is the explosion that happened at the factory of Laporte Industries in London. It's a long time ago now, back in 1975. There was an alkaline electrolyzer in the plant, which of course produced hydrogen by, in this case, electrolysis of a potassium hydroxide solution. Potassium is what we in Norway would call kalium, but it's the same thing. The process also, of course, produces oxygen, which was then discharged as a waste product. There was a stress crack in the oxygen separating drum in the electrolyzer, which resulted in flow of hydrogen and electrolyte into the oxygen separating drum. And of course, meaning that meant that oxygen and hydrogen would mix and would form a flammable mixture. And this was ignited. The consequence of this explosion was that the plant operator died due to injuries. Actually, they were burns from the alkaline, liquid alkaline, the potassium hydroxide. The lightweight roof was almost completely blown off the building. There was no damage outside the factory, but there was considerable damage to the electrolyzer. So what caused it? Well, first, electrolyte passages, they were blocked by sludge. And these were responsible for admitting electrolyte at the bottom of the cells. This blockage caused a reduction in electrolyte flow. The velocity of the electrolyte increased where the passages were partially blocked, which then caused eventually corrosion and erosion of both the electrode gauzes due to hydrogen embrittlement, and the separator suffered from physical breakdown, resulting in the mixing of hydrogen and oxygen, which ignited and caused this strong explosion. The explosion could have been prevented, or as it says, it wouldn't have occurred if the manual gas analysis for purity of the oxygen produced had been carried out diligently, if there had been a system for checking the accuracy of the gas analysis recordings, if the dangers from failure to carry out oxygen analysis had been emphasized to the operators, if the plant had been kept shut down until the cause of previous issues had been determined, and if the cause and effects of sludge formation had been more thoroughly investigated. So this all points to the importance of process safety and hazard awareness, and the importance of operational checks, inspections, and maintenance. There is an ICME report that you can find online, which really goes into detail about this accident and the findings. Another one, there was an explosion at an ammonia plant in Norway due to a hydrogen leak inside a building. This was back in 1985, still a long time ago. Hydrogen was produced at the ammonia plant by partial oxidation of a heavy hydrocarbon fuel. The total amount of hydrogen released was estimated to be between 10 and 20 kilograms, which meant then, because 1 kilogram of hydrogen at normal conditions would be about 12 cubic meters, so 100, 200 cubic meters of hydrogen was released. The energy content of 1 kilogram of hydrogen is equal to about 30 kilograms, almost 30 kilograms of TNT, but not all of this energy that is released when hydrogen explodes is released in the form of a blast wave. So it was estimated that the explosion was equivalent to between 100 and 200 kilograms of TNT. So a strong explosion. 2 employees died. There were broken windows and structural deformation and damaged walls, and several windows shattered within a 400 meters radius. A roof was lifted up on this construction to a height of 1 meter. If I remember correctly, this was actually a concrete roof. I'm not quite sure, but I think it was. The side walls were blown out at 60 meters. This factory never went back into production. The severity of the explosion and the subsequent fire could have resulted in a far greater loss of life than what happened. But the incident occurred on a Saturday, and there were few people in the area. So what caused this accident? The main explosion took place in the purification section of the hydrogen plant. This section contained a wash tower where CO2 was being removed from hydrogen by absorption in water. The accident was triggered by a gasket in a water pump blowing out, which occurred when operators were trying to change from one pump to another. Here I call it from pump B to pump A. Unfortunately, they did not observe that the valve in pump A was closed. So the water supply from pump A was too low to maintain the water level in the absorption tower, resulting in automatic shutdown. A second attempt to start pump A resulted in higher vibration level than normal. The operators discovered that the valve was closed. They tried to open it, but failed due to the large pressure difference that was observed. A backflow of water traveled to the gasket, bringing the hydrogen with it. The system was designed to prevent backflow, but it didn't function as intended. So hydrogen, now mixed with air, formed a combustible gas cloud, which easily ignited and exploded due to the low ignition energy common in accidental releases of hydrogen. To ignite hydrogen by a spark requires a spark with the energy about 1/10 of what is required to ignite, for example, natural gas or methane, and propane for that matter. So it's very easily ignited by spark. The hydrogen cloud, it ignited due to, actually in this case, the heating in the pump that worked against the closed valve. As a consequence of the explosion and the blast, the roof lifted and it tore off a pipeline coming from the wash tower, resulting in a jet fire. As is illustrated on the drawings on the right there. This drawing is actually taken from the gas explosion handbook, which was written by Gexcon many years ago now, but as a introductory text to explosions, I can still recommend it, and you can find it. It's downloadable from the Gexcon webpage, is free of charge. So what did we learn? Well, the investigation concluded that the accident occurred as a combination of operational error, technical failures, and weakness in the design to mitigate failure mechanisms. So a key issue here was that the design was actually vulnerable to human error. The third accident and final one I'm going to talk about here is a hydrogen tank explosion in South Korea 5 years ago. So what happened there? Well, an outdoor tank containing hydrogen gas exploded at the research and development complex during the test of a water electrolyzer, which was coupled to a renewable energy system. 2 men died, 6 were injured, and several buildings were severely damaged up to 100 meters away from the explosion. The equivalent TNT mass in this case was estimated to be about 50 kilograms based on observations of the damage nearby. So what caused this? Excuse me. A pressurized alkaline water electrolyzer was under test to evaluate intermittent renewable energy duty cycle performance. The electrolyzer's cell membrane suffered from degradation, which permitted excessive oxygen to permeate into the hydrogen storage tank. So the hydrogen then mixed with the oxygen and formed an ignitable mixture. The mixture ignited within the tank, resulting in an internal explosion. The source of the ignition was unclear, but there is some belief that it could have occurred due to auto-ignition, so by itself, or an external spark. So we don't really know. The damage that you see on the photo here is quite typical of explosion damage. It is mechanical rupture and deformation of structures. It is different in that sense from fire damage, which could be more like melting, at least when it is steel or metals that are exposed to the heat in the fire. The investigation concluded that better understanding was required of the connection between membrane gas permeability, degradation, and the dynamic operating range of the project when establishing process safety control. Consideration should be given to automatic actions, such as storage isolation, stopping gas generation when safety limits are exceeded, such as flammable gas mixture, excessive cross-cell differential pressure, and other applicable process safety limits. So the key issue here is to understand potential failure mechanism, know the safe operating limits, and take actions when exceeded. All right, that was the first part. Now I go on to hydrogen safety characteristics, fires and explosions. That means to learn more about the physics and chemistry of when things go wrong with hydrogen. Hydrogen is different from substances like hydrocarbons, for example, and needs to be handled differently. It is extremely buoyant. It is odorless and non-toxic, which means that it's not easy to detect by people. It is a gas at ambient conditions. It can be a liquid if you cool it down below the boiling point, which would be around 20 Kelvin or minus 250 or so degrees Celsius. It has a very wide flammability range, which means that you can ignite it almost at all concentrations. If you compare with methane, methane is flammable between 5 and 15% by volume, whereas hydrogen is between 4 and 75. Now, you will not get an explosion if you have a hydrogen air gas cloud at 4% by volume or at a concentration of 75% because it will be burning so slowly. But it may ignite and the flame may propagate to other parts of the cloud where perhaps the concentration is nearer to the stoichiometric concentration, which is around 30%, and then give rise to an explosion. But you need a strong ignition source to ignite hydrogen at the flammability limits. Molecules are very small, so hydrogen leaks easily. And hydrogen burns fast, much faster than most hydrocarbon gases, which means that it can give rise to faster flames, which would give you higher overpressures in an explosion. I mentioned already the low ignition energy, 0.02 millijoule. That is a very low energy. Most electrical equipment can, if sparks are generated, exceed these kinds of energies by order of magnitude, I guess. Hydrogen also has the characteristic, I should say, that when hydrogen under pressure leaks to the atmosphere, it doesn't cool like most gases that we experience, but it actually heats up due to the so-called negative Joule-Thomson effect. It has been speculated whether this can be a possibility for auto-ignition of leakages from high pressure, but I haven't done them by myself, but I've seen calculations which indicate that the heating from the Joule-Thomson effect is not sufficient to actually bring the hydrogen up to ignitable temperatures. We're talking about maybe a few tenths of degrees, but we actually need to go to 500 degrees or more to ignite the hydrogen. But we need to know about the characteristics or the peculiarities of hydrogen to be able to develop designs and operating procedures so that we can implement it as an energy carrier without unacceptable societal risk. Here is just a video which shows a blevy boiling liquid expanding vapor explosion. This was liquid hydrogen in a container which was then heated by a fire from outside. So these levies is something that can happen with other fuels, and it also can happen with hydrogen. Okay. In GEXCON, we did a few years ago a large number of tests where we tried to make configurations to mimic vehicle fueling compressor stations, as is indicated here. I think we bought something like 70 containers, 20-foot ISO containers, and we basically blew them up. I would like to make note of the sealing in these containers, where we removed the sealing and put in some framework to be able to accommodate explosion vent devices, meaning weak plates which would open up very early in an explosion due to the low pressure experienced at the beginning of the explosion, so that the overpressure would be vented out of the enclosure and thus relieving and reducing the maximum overpressure that could be experienced. Here's a video showing such a test. 24% by volume, so lean, but relatively close to stoichiometric concentration. And you saw a door from the end of this container flying through the air, and you can also see the shape of the container is now different. Here is a high-speed video of the same. So this explosion was approximately 1 bar or 1.1 bar um, overpressure. So compared to atmospheric pressure. From another angle, so this is an illustration of what can happen if you confine hydrogen. Remember, I mentioned that hydrogen is light, so it would tend to move upwards. But if you actually contain it in a container like this, then it will not be able to disappear or spread out and go away from where the explosion happens. So one of the learnings, one of the things that one should think about when it comes to hydrogen safety is that don't collect it inside something. Try to have open structures so that it can disappear, that it can disperse because of its buoyancy. It will do that. Here I have two videos also showing identical setup. Now with these explosion vent panels on the top on the ceiling, as you can see from the pictures here. The left video is 12% by volume, and the right video is 15% by volume, so slightly higher concentration on the right-hand side, but still lean, far away from stoichiometric. You will see that the left one with the lower concentration is slower and weaker, and the right one is faster and stronger. You can see, you can judge that based on the speed of the opening of the panels. So this is slow, and this is faster. It's quite clear. So a relatively small difference in concentration will give rise to a stronger explosion. So what is the point of doing this? Well, if we have these panels, then, as I said, they will open up early in the explosion before it has developed to its full potential, and so the pressure inside will be relieved, and thereby we will actually reduce what can be the maximum pressure inside the container. So that is what we call explosion venting or explosion relief. We don't know everything that we should know or need to know. But the research is ongoing at many places, in Gexcon and other places as well. There is a lot of research going on to try to understand hydrogen better so that we can use it safely. I will not read through this list. I assume that you will receive the presentation after as a PDF after today's webinar. But it is clear that experimental work is needed. Model development is required. To date, as far as I know, the FLAX 3D software is the only CFD-based safety analysis software which is validated for hydrogen. And as knowledge pours in or is developed, new experimental results will be implemented in the software. I will show you this video, which is on the left-hand side. It is infrared video. On the right-hand side, it is normal electromagnetic visible light. So what you will see is that when we inject liquid hydrogen into a water reservoir, the hydrogen evaporates and comes up as a cloud from the water, and after some time it ignites. You don't see that on the right-hand side because of the radiation from hydrogen flames is very limited, but you can easily see it in the infrared spectrum on the left-hand side. The two videos are exactly the same. It's just that different frequencies are being recorded, different electromagnetic frequencies. So Now we start the injection of liquid hydrogen. There it ignited. You can see on the left, you can barely see it on the right, but it's very weak. But on the left, you can see it very clearly that the hydrogen cloud above the liquid surface ignited. So the question that immediately came up was, why did it ignite? Because we didn't have an ignition source. There was nothing there that could explain that it ignited. But this test was repeated more than 30 times, and in more than 70% of these tests, ignition happened without the any known ignition source. And it is clear, if you want to do safety assessments and use hydrogen in a safe way, these are things that we need to understand. Why does it ignite? So how does hydrogen compare to other gases? This is some of the early work that Gexcon did on hydrogen back in 1988, when we tested different gases and looked for their maximum overpressure potential. So we had a tank, which was like a pie-shaped tank like the one you see here, 10 meters long. And we filled it with stoichiometric fuel-air mixtures from methane via propane, ethane, ethylene, and hydrogen. And what you see here is that for this particular scenario, these are the maximum overpressures seen for these gases. Hydrogen was clearly the worst with 8 bar overpressure. Ethylene was around 2, and so on. Methane was the weakest. This does not mean that methane gives weak explosions in general, but for this particular scenario, these are the results. So it is clear that hydrogen has a potential to give stronger explosions than, for example, many hydrocarbons. And that needs to be taken into account when you do safety assessments and safe designs. I have a few videos, I think I have time to show them, which are not from hydrogen explosions, but they illustrate which parameters influence explosion strength. That will be the same. These will be the same parameters, whether you have methane or propane or hydrogen for that matter. The main difference with hydrogen and the others is that it is more reactive, hydrogen, it ignites more easily, and it burns faster. So I will now show a video of 3 explosions, and there is a permeable panel on the end of this module, which will blow off if the explosion is strong enough. So the 3 explosions where 0.3 bar overpressure is the first one, the second is a half bar, and the third one is 1 bar. From lean methane air to stoichiometric methane air to stoichiometric propane air. Propane is worse than methane in terms of overpressure. 0.3 bar, nothing much happened. You can design for 0.3 bar. Half a bar, stronger, as you can see, and the panel fell off. And 1 bar. Now, 1 bar is a relatively strong explosion, and it can be quite expensive to design for a 1 bar explosion overpressure. Here you see the panel ended up in the forest around 40 meters away from the test facility. Now, effect of congestion or pipework or whatever you want to call it. On the left-hand side, there is a video of an experiment with a few large pipes. On the right-hand side, there is a video with many small pipes. In these 2 tests that I will show you, the amount of gas, the type of gas, the ignition location, everything is the same in these 2 tests, except the pipework is different. And the reason why we get different results is due to turbulence generated by the multitude of pipes that you have here in this case. You see an arrow pointing down. The pressure from this test was about 0.02 to 0.03 bar, whereas for this one, we got between 3 and 4 bar overpressure. So let us look at the videos. So when you when you consider designing a facility involving gas, flammable gases, and also hydrogen, then remember this, that the congestion that you put in there in terms of pipework and so on will influence how strong an explosion can become. Another couple of tests, these were done by DNV-GL. We had a 45-meter long rig containing pipework, and there is plastic around the rig. Oops. There is plastic around the rig to contain the gas because we fill the rig with gas and then we ignite it. And the first one is obstacles along the whole rig, and you can see the flame starting to burn on the left-hand side, and then it accelerates and goes faster and faster. And it is so that the faster the flame is, the higher the overpressure is. You could clearly see the acceleration of the flame to quite high velocities. Then let us look at the second one, where the second half of the rig is filled with gas, but no obstacles, no pipework. You see that the flame slows down and burns really slow, just maybe 5-10 meters per second or so, which would not give rise to any overpressure development. So obstructions, as I said for the previous slide also, they influence explosions also with hydrogen. Then we have there are two different types of explosions that we normally consider. There are deflagrations and detonations. I will not go into detail about what they are, but these ones were deflagrations. So they can have flame velocities from tens of meters per second to a few hundred meters per second, and you can have overpressures in the range of from millibar and up to a few bar. If you have a transition from a deflagration to a detonation, then you can have suddenly flame speeds not in the few hundred meters per second that you see down here on this graph, but you can have it in kilometers per second up here, and you have very high overpressures, tens of bars of overpressure. So it's a much worse explosion than a deflagration. And hydrogen is prone to detonation, so you don't really want a strong deflagration that can transit into a detonation with hydrogen. So let me see the video. This was the detonation, much faster and much stronger than a deflagration. All right, so that was a little about characteristics related to fires and explosions and what to think about, to consider. Now I will pass on to analysis and control of risk. As you have seen now, hydrogen does carry inherent risks, such as flammability and explosiveness. We still believe, however, that with appropriate safety precautions, these risks can be managed effectively, but we need to understand what makes the hydrogen tick. What is the difference between hydrogen and other gases? And that is very important. Hydrogen safety technologies have improved, such as leak detection systems, hydrogen sensors, improved storage and transportation methods. But we still need to consider safety elements like comprehensive risk assessments, safety planning and design, rigorous training and education for personnel, regular maintenance and inspection, emergency response protocols, robust incident reporting and investigation procedures. By integrating these safety elements into hydrogen projects, the likelihood of accidents and consequences can be minimized. We expect that hydrogen is not really inherently more dangerous, but it is different. And we need to understand those differences such that we can design and operate according to them. That is very important. This slide is about hydrogen safety resources. Ensuring safe and responsible use of hydrogen requires addressing safety concerns associated with both production, storage, transportation, and usage. And these safety resources, they play a crucial role in assisting engineers, researchers, and safety professionals in making informed decisions, implementing appropriate safety measures. I have two examples of safety resources mentioned here just to illustrate. H2 Tools is a software suite developed by the Department of Energy that offers access to a range of resources, including databases, calculators, and models for evaluating hydrogen hazards. Flax CFD software is a state-of-the-art tool for analyzing consequences of different scenarios to develop safe design solutions and to mitigate hydrogen risk through the hydrogen value chain. So how do we harness the potential of hydrogen and still minimize risks? We have to adhere to regulations and standards. We have to learn from historical incidents. We have to implement safety elements as those mentioned in the previous slide, and we have to utilize safety resources as mentioned above here. By prioritizing safety, we can unlock the full benefits of hydrogen as a sustainable energy solution. When we do or want to do hazard and risk assessment for hydrogen, it's not really that different. The methodology is the same as we have used elsewhere in oil and gas industry, for example. It is just that we have to understand the hydrogen physical and chemical characteristics that makes hydrogen different from, for example, methane. So these tools that are mentioned on the right-hand side here, they are applicable in the hydrogen value chain. And they are, for example, hazard or rapid risk ranking. This list here is in the order of increasing hazards and complexity. So a hazard would typically be a starting point to identify hazards and rank associated risks. Then HAZOPs, hazard and operability studies, and or FMEA, analysis on impact of process deviations and failures on hazards, functionality, and operability. Then you have LOPA and SIL assessments, identification of critical scenarios and assessment of independent safety functions. And finally, QRA, which is the most complex way, quantitative risk assessments, which involve calculation of risk and comparison with relevant quantitative acceptance criteria. When you do QRA, you can also compare risk-reducing measures, and based on the calculated risk, you can choose the risk-reducing measures that are the best for your case. Process safety assessments are, of course, done in early project phases, like concept selection and pre-feasibility, as in the design development project phases, which is feasibility, front-end engineering design, and detail design, and in the operations project phases, We have commissioning, startup, normal operations, turnarounds, and decommissioning. I will not go into detail about what these involve, but you can have a look at it when you receive the presentation at a later stage. The third or the most complex analysis method I mentioned to analyze risk was QRA. Typically in QRA, you tend to use computational fluid dynamics, so three-dimensional CFD, computational fluid dynamics simulations. And one important aspect of that is that you can, as I mentioned, actually analyze the effect of risk-reducing measures. For example, in this case, you see an experiment where we have these explosion vent panels on top of the module. That is the experiment. And below, you see the simulation, which shows you how the software, the 3D software, would analyze the scenario. And here we can, for example, test and model the effect of having different weights of panels. We can have different numbers of panels, sizes of panels, locations of panels, and so on. All of this can be analyzed by simulating using 3D CFD. It is, of course, much cheaper than doing the experiments. So that is why it is done. We can't always do experiments every time we want to design safety features. So let us look at the video. Now, of course, this is just an illustration showing the experiment and showing the same output from the simulation. But in addition to this nice graphic, in the simulation, you will get the pressure development inside, you will get the flow velocities of gas out, and so on. So you can see if we now, instead of 6 panels, we have 4 panels, you would probably see that the pressures would go up inside the simulation module. If those pressures are acceptable, it means that it is maybe enough with 4. If the pressures are too high, you may have to use 6. This is the kind of evaluations you can do using CFD. So then the final part is about safety standards and regulations. Regulatory bodies worldwide, they have been developing guidelines and standards specific to hydrogen technologies, covering production, storage, transportation, and use. And adhering to these standards helps create a consistent and safe operating environment. Now, this is not done work. This is under development. So guidelines are being developed, to some extent have been developed, but more work is required, amongst others, to understand the behavior of the physical and chemical behavior of the hydrogen. In the US, codes and standards for hydrogen facilities are developed and maintained by, for example, the NFPA and the Department of Energy. The NFPA has published the NFPA 2 Hydrogen Technologies Code, addressing the design, installation, operation, and maintenance of hydrogen systems. And the DOE develops safety guidelines and supports research and development to advance hydrogen safety. There is also something called the Hydrogen Safety Panel, which brings together industry stakeholders, safety experts, and researchers to provide guidance and support for hydrogen safety, focusing on safety challenges and sharing best practices and promoting safety awareness. There are a number of standards that are relevant, even though they are not hydrogen specific, like quality management, risk management, area classification, integrity of safety instrumented systems, and so on. As I said, they are not hydrogen specific, but still relevant. Then you have international standards which are H2 specific. Typically, that can be what I already mentioned, the Hydrogen Technologies Code. Then you have ISO 15916, which is basic considerations for the safety of hydrogen systems. ISO 19880, gaseous hydrogen fueling stations, and so on. I won't go into detail about this. I will just mention them so that you are aware of them and can look them up at a later stage. And there are more than these also. I should perhaps mention that GEXCON and Greenstat, who is the organizer of this webinar, we are working together with the Norwegian regulatory authorities in a project where we are cooperating with Indian authorities to develop hydrogen safety regulations. So that is ongoing work at the moment between Norway and India. Best practice. Well, what we see is that there are new applications coming up, new uses of hydrogen. We see that the development of knowledge in the industry is very rapid, more rapid than the update and development of standards and regulations. This means that we should always think about having safety margins when we in our design, because we outlearn the textbooks. It is at least in our part of the world here, accidents involving hydrogen may have a severe negative effect on the social license, and lead to negative public sentiments about hydrogen if large accidents occur. So it is important to ensure that the accidents are as few as possible and that they are not severe. So companies involved with the hydrogen value chain should pursue and promote safety improvements beyond standards and regulations. They should promote cross-industry learning, so sharing is extremely important, and ensure that all stakeholders are aligned to the safety objectives. I had one more slide here, which I was looking for. In 2019, the European Hydrogen Safety Panel published a guidance document for safety planning for hydrogen and fuel cell projects, in which the safety panel experts extracted 10 safety principles from the actions required to prevent an escalation of a prototypical hydrogen accident. The derived safety principles, as listed in this table, they state simple objectives being widely understandable and acting as preventive barriers, or at least as risk-reducing measures on various elements of the chains of event. And they would be typically, I'll read quickly through them: limit hydrogen inventories, avoid or limit formation of flammable mixtures, carry out ATEX zoning or hazardous area classification analysis, combine hydrogen leak or fire detection and countermeasures, avoid ignition sources, avoid congestion. Remember the effects of congestion on explosions. Avoid confinement. We don't want to collect the hydrogen, we want it to go away. Provide efficient passive barriers in case of active barrier deactivation. Train and educate staff in hydrogen safety. Report near misses, incidents, and accidents to suitable databases, and include lessons learned. Adequate design and material selection. So these were the 10 safety principles extracted by the European Hydrogen Safety Panel. It's good advice. For a number of years, I was involved with the IOGP as chairman of the Process Safety Subcommittee. That's why I mention it here. It is not hydrogen specific or even hydrogen related, but it is very, very good advice when it comes to operating management system frameworks, barrier definitions, key performance indicators, and so on. So how to manage risks in an environment where there are, which handles, for example, flammable substances. So I would advise you to go to iogp.org and look up this information. Some of these relevant reports that I think are good reads, they are shown on this slide. So, to conclude, what is the way forward for hydrogen and safety? There are some points that I want to share here. I think they are very important. You should integrate contributions from important stakeholders like regulatory bodies, research and teaching institutions, funding industry, and other relevant knowledge partners. Fundamental knowledge is still required and needs to be developed. Remember the ignition from no ignition source. Knowledge that you develop should be codified into software so that you can actually do, for example, consequence analysis, looking at the effects of risk-reducing measures. You should develop and verify safety best practices. You should have a focus on teaching. Universities should teach students, and the workforce should be developed, which is competent with regard to hydrogen safety. I have heard numbers saying that in India you need maybe 100,000 or I don't know, a large number of safety engineers to manage what will be required in this hydrogen economy that is coming up. You should contribute to development of laws and regulations. Regulatory bodies are and will be required to audit, investigate, and ensure compliance to laws and regulations. As consultants, we should apply knowledge and tools to industry and to government. And in general, throughout the value chain, we should build capacity to manage. We shouldn't have 5 people sitting there and controlling applications from industry and handling hundreds per day. It's not feasible. The work is not done well. All right, that is the end of my presentation, 1 hour. Thank you very much for your attendance.
Thank you very much, the young Roar. It was an excellent presentation. I would like to say a few words about your presentation, which I think was quite engaging, but also a testament to your profound expertise and experience in this field. The way you went through it systematically, the subject of today, safety. I think that we have learned from past accidents in the hydrogen sector, which provide us with invaluable insights. And I think that through these lessons that we can also shape a safer and more secure future for our endeavors in the hydrogen technology and projects that we are going to implement going forward. Hydrogen, we know with its incredible potential of clean energy carrier, comes with its own sets of challenges, as we all know. And I think you, Jan Roar, masterfully explained us the complexities and degrees of hydrogen safety, offering us a comprehensive understanding of the measures necessary to mitigate risk effectively as well. And I think that the real world examples that you shared with us highlight the importance of learning from history. And by studying incidents of the past, we can construct a roadmap toward the safer practices, ensuring the responsibility and sustainable development of hydrogen technologies. And I think that when you mentioned also the work that we are doing together with the Indian authorities and MNRE, I think that showed that we all need to come together to work on these subjects, because they are not stagnant. They are, as you would pointed out as well, continuous research that is needed, and exchange of knowledge and experience in the different pilot projects that is now implemented around the world. There is a lot to be learned. And I'm quite certain that each one of us, either we are experienced professionals or newcomers to the field, have gained a valuable takeaway from your sessions today. I think your ability to communicate complex safety principles in a clear and accessible manner has undoubtedly contributed to our collective knowledge today. And I will also, on behalf of Green Start and USAID and PDSL and our partners, extend a sincere appreciation to you, who I have known for a long time. We have been working together, and you were also my right hand as a senior vice president in GAXCON. And I was quite happy when I was able to recruit you back to the GAXCON, where you started your career as well, when you went out from the university. So we are really graced today with your expertise, and the contribution has undoubtedly deepened our understanding of the hydrogen safety. And we are grateful for your time and efforts that you have invested in sharing your knowledge today. So thank you again, Jan Roar, for this enlightening session. And